In this video, we're going to be looking at conservation of momentum and mechanical energy. Really, what we're going to do is we're going to combine situations where we can conserve mechanical energy and new situations where we can conserve momentum. Specifically, situations where one law applies, then the other law applies, and there's a link between them. So an interesting scenario is something we call a ballistic slider. If you've watched any procedural crime drama or any other movie about a mystery, or even an episode of Mythbusters, you've probably heard of ballistics, which is really the study of projectiles. Usually we're talking about like guns and arrows and weapons, but it really is just the study of anything that is fired from some sort of projectile launcher, and then what those things do as they travel through the air or when they impact other things. So if you were to take an object, a block, and fire a projectile into it, you could look at how the object moves after the collision and work backwards to talk about what happened with the launcher itself. So what are the key events here? And what conservation laws apply to each event is really how we want to consider these things. The key events are the ball, travels through the air. So there's kind of three we could talk about. There's the launch itself, whatever goes on inside the launcher, but that's hard to understand because we can't take it apart. So really the first event is that there's an impact between the two objects. And then once they're together, they slide across the table. So the first event is the spring launches the ball. The second event is the ball collides with the box. The third is the box and ball skid to a stop. So what is the conservation law that applies for each of them? Well, for the spring launcher, that's conservation of energy. Spring potential gets turned into kinetic, right? We start with potential, we end up with kinetic. When the ball collides with the box, this is a conservation of momentum. It's a collision problem. It's a totally inelastic. They stick together. And then we have the box and ball slide to a stop. And so that's going to be a work non-conservative. You can either solve it as a work kinetic energy theorem or in this conservation of energy with a non-conservative term method. There's no potential energy anywhere. There is kinetic energy at the beginning, but not at the end. And then there's work done by friction to stop it. So each piece actually would give you something for the next piece, right? If you were able to know the velocity of the ball before it hits the box, then you could plug that into the initial momentum. And then you could use that to find the final momentum. And then you could use that velocity to plug into the kinetic energy initial to get to the final distance traveled. But the reality is you're probably going to know about how far the box skids and work backwards up from 3 to 2 to 1. So what are our conservation laws? Well, in energy conservation, we have the conservation laws. This works for anything where there's only conservative forces. And then we have our non-conservative work version of it, or we can use the work kinetic energy theorem, right? For momentum conservation, momentum initial equals momentum final. That could be in any dimension, x, y, or z. These are vectors. And this criteria is no net external forces, or this happens really quickly. And that would be the case of the ballistic slider, right? There is friction on the box, but the collision happens quick and then it slides is a way we can think about it. So a collision of cars or something, projectile exploding, that kind of thing. So how do we do this? The key thing is to know when to apply the law. And this is true in all of physics, right? You need to know when to apply the law, not just what the law or equation says. I'm going to do two examples. So what we have to do is we have to identify the key events, and we have to apply the correct conservation law to each event. That's the big thing. So here we go. We have a block sliding across a frictionless table. Then it hits another block, and then things fall off the table and become a projectile, right? We are told that we have a final velocity of 15 meters per second at the end. And mass 1, moving at 30 meters per second, collides with M2. They stick together, becoming one final object. And they land on the ground with a velocity of 15 meters per second. What is mass 2? So two events, right? And that's how these kind of things work. The first event is the collision. The second event is projectile motion. In the collision, we get momentum conservation. In projectile motion, we get mechanical energy conservation. So where do we start? Well, the thing we don't know about is M2, and we don't know the velocity of block 2 and 1 together after the collision. So the collision we don't really know very much about. So we're going to have to work backwards. We're going to start with projectile motion. And normally with projectile motion, you might think of this as a problem where you would use kinematics. But since we're talking about conservation laws here, we're going to use this. I don't actually care about how long it took to fall. All I'm interested in is what was that initial mass. There's no gravitational potential energy at the end, so we should be able to solve for the initial velocity just before the blocks left the table in using this method. Everything cancels out and you end up with 11.3 meters per second. This is the velocity of the projectile motion at the top of the table, but that is also the final velocity for the collision, right? So that's what's going up there. That is how fast blocks 1 and 2 are moving after they collide. So kind of resetting again, now looking at the collision. Well, in the collision, momentum of the first object plus the second object before equals the combined momentum after. And solve for M2 and we get 6.7 kilograms. Another type of device where we can do this is what's called a ballistic pendulum. So instead of it sliding, a projectile hits a block, and you can see this here in this video. You launch this sort of a spring-loaded launcher. It sticks into that, and it pushes a marker up a certain distance. And so that's an angle measurement. But of course, knowing that angle measurement and the length of the pendulum, you could figure out how high up it went. And that would be something you could say, oh, well, how high up it went, and knowing the mass of that wooden block would allow me to work backwards and figure out how much potential energy, therefore how much kinetic energy, etc. So we can solve one of those problems, right, like this. A 20-gram bullet is fired into a 2-kilogram pendulum, causing it to swing upward. We know we're going to start with something we know on this side. The muzzle velocity of the bullet is 250 meters per second. How high does the pendulum go? Well, again, 2 events. There's a collision followed by the upward swing. In the collision, momentum is conserved. So we have a 20-gram bullet. We have a 2-kilogram block. The block was at rest initially, so there's 0 momentum there. It was all the momentum in the bullet. And so the velocity of the objects just after the collision is about 2.5 meters per second. That becomes the initial condition for our swing upward, right? The V prime from the collision is the V initial for the pendulum swing. Conservation of energy. Notice it's the total mass that's swinging upward, M plus M, big and little together. But it doesn't really matter because they cancel out here because the same mass is moving in conservation of energy. And so we end up with 0.31 meters as the height up to which it swings. All right, so there's some examples. There's plenty of practice for you, but the big idea here is that some problems have a part where mechanical energy is conserved and another part where momentum is conserved. And our goal here is to put those two together and solve interesting problems.